Welcome back everybody to our course on memory device technology for AI/ML computing. I'm your instructor Dr. Shubhadeep from Electrical Engineering at IIT Hyderabad. Today we will begin the second part of our course, which will look at futuristic memory device technologies for facilitating more brain-like computing or neuromorphic computing. So today's module 6, we start by having a brief introduction of what are electronic non-volatile memories, specifically what are two-terminal ENVMs. As we have discussed, ENVMs are sometimes interchangeably also known as storage class memories. Let us remind ourselves why they are called storage class memories. Before we start any module, we generally look at the devices that we are going to look at. Where will they be actually placed in the memory hierarchy? Remember, this was your pyramidal memory hierarchy with your CPU logic subsystem right on top and closely followed by your L1, L2 and L3 caches, which are made by your 60 high performance SRAM cells, followed by your main memory, right? So your main memory was your DRAM arrays, which had at its cell level 1T, 1C. And traditional computational systems, there is nothing called storage class memory. That's why I have written it is emerging. This is followed or directly interface with NAND flash. So NAND flash is just one transistor. It has very high bit density for reasons that we had been discussing this week and last week. This forms the primary storage. Okay. So where do storage class memories fit in? Storage class memories fit in right in between the main memory and the primary storage. So a natural question which may come to our minds is, why are we looking at these emerging storage class memories or emerging ENVMs or electronic non-volatile memories? Our main memories and primary storage both are in very matured state. Yes, of course, there are some scaling challenges, but why do we really need to look at storage class memories in the first place? So if you ask this question, probably just having this diagram does not give you a lot of justification, because this diagram is not to scale. So we have to look at some actual quantitative numbers. And let me remind you of these quantitative numbers. This is something that we have already studied, but let us look at the so-called IO bottleneck. So the IO bottleneck originates from noting that there is a large gap in latency when we look at our main memory DRAM subsystem and secondary or primary storage flash or SSD subsystem. Okay. So whereas the latencies in DRAM is roughly in the order of 10 to 100 nanoseconds, for flash, NAND flash, especially NAND flash storage subsystems, this latency goes to almost 0.1 to 10 millisecond. Now please note, this is almost 4 to 5 orders of magnitude difference. So the latency mismatch is in the range of 4 to 5 orders of magnitude, and that is what we described as the gaping hole between the memory subsystem and the storage subsystem. Okay. So the idea of ENVMs is hopefully to bridge this gap. Okay. So that is why they are called storage class memories. Storage class memories aim to remove this difference, very strict difference between main memory and secondary storage. Okay. Also, we will see that generally, not always, these ENVMs, we plan to make them two-terminal and non-volatile. So non-volatile is generally a very strict conditions. Sometimes ENVMs can also be three-terminal, but we will mostly focus on two-terminal ENVMs. Why is this the case? To answer why this is the case, let us have a review of the IO bottleneck that exists, that great divide between DRAM and flash in terms of latency, in terms of throughput, and especially in terms of cost. Okay, so let us look at the diagram in front of us. from few different angles. First is, let's look at bit density. Okay, so bit density in DRAM due to scaling, of course, has been quite good. I put one smiley face because it is not as bad. It is not excellent, but it is not as bad. It is not as bad as your SRAM subsystem. Okay, but NAND flash, I have put 3 smileys. I hope you recognize why these 3 smileys are there. First smiley is for 4f squared. The NAND flash cell array is 4f squared. The second smiley is for bit scaling. And the third is the transition from 2D to vertical 3D scaling. So bit densities in NAND flash are really incredible, as we have seen in our previous module. And that directly affects your cost per bit. It may so happen that NAND flash might be slightly more expensive chip wise or die wise compared to DRAM. But when you look at cost per bit or price per bit, NAND flash beats DRAM by a very big margin. So these numbers are not really updated, but we can see that NAND flash beats DRAM in cost per bit to the tune of 1:7 or even 1:8. Okay. But where NAND flash really suffers is latency and performance. We see that DRAM subsystems, at least at the internal subsystem level, we can achieve read and write latencies in the orders of tens to maximum hundreds of nanoseconds. In NAND flash, to get high density generally comes with 3D NAND plus MLC, TLC or QLC. The latencies are really, really large. We know erase latencies are in the order of 1 milliseconds, but even read and program latencies are in the orders of microseconds to hundreds of microseconds. Okay, tens to hundreds of microseconds. The other big advantage that NAND flash has, and that is why it is called storage, is non-volatility. So DRAM is just a capacitor and a transistor. Capacitor leaks very quickly and you have to keep refreshing. So therefore NAND flash is non-volatile. The charges which are stored in the charge storage layer through the control gate remain almost forever, right? And this refresh, continuously doing the refresh, is what results in much larger power burn. Okay, and that is what is indicated in power per GB at maximum bandwidth. So as we see, the difference in power burn between NAND flash and DRAM is closely 4 times. The final thing that we will look at is the bandwidth, notwithstanding the much lower read latency. If you see, the read latency was several orders of magnitude different, but the bandwidth is not so terrible. The bandwidth is only, as you can see, roughly 40 times. Why is this the case? Remember, in NAND flash, at a time you access large chunks of data in and out of the system. So that is why, although the latency is really poor, the bandwidth is somehow managed. So this was our very quick review of the IO bottleneck. This huge throughput difference of nearly 40 times is what creates the IO bottleneck in the first place. And the pinch of the IO bottleneck was not really felt when we were in the era of logic computing paradigm, where you were just doing number crunching and data was very less frequently taken from the storage subsystem into the main memory. There the main bottleneck was between the CPU subsystem and the main memory subsystem. But as you enter into the era of AI/ML computing, which is your data-driven computing, the pinch of the IO bottleneck is much, much adverse. You are feeling that pinch very, very significantly. That is the reason why we have started to look at other forms of memories, such as storage class memories, that can fill this large divide between bandwidth and in the bandwidth of DRAM and NAND flash, right? So as we discussed, as computing paradigms change and computing requirements change, even the devices that will be used for computing will also change. these devices, as new devices are invented, they will be implemented in different parts of the memory hierarchy. So what is the goal of eNVMs or SCMs, storage class memories? Now let's look at it from each and every angle. So first, let's look at bit density. The goal of eNVMs is definitely to have higher bit density compared to DRAM. But I doubt, of course, the jury is still not out on it, but I doubt that you will be able to achieve much larger bit density compared to NAND flash. One, because it is a mature technology. Other reason is that the 3D NAND configuration is something very, very remarkable, and we yet need to see whether this kind of 3D packing is possible in eNVMs. But as we will see, in eNVMs, it is very, very much possible to have multi-level cells, or you can store multiple bits into the same physical cell. Okay? And because we are not very sure about the bit density, right now commenting about cost per bit is going to be very challenging. And this is the main challenge. What keeps eNVMs from realizing this goal? As we know, all that industry cares about is what is the final cost per bit. If the cost per bit is not that suitable for them, they will never commercialize, right? So the cost per bit is the limiting factor, as I see it, in the commercialization of eNVMs and the widespread use of eNVMs. The other thing that we want to achieve through eNVMs is the most important divide, which was in bandwidth or latency or in performance. We saw that DRAM latencies are in the order of 10 to 100 nanoseconds. The goal of eNVMs is also to achieve the same, to have 10 to 100 nanoseconds, whereas in NAND flash, we know it is in the order of microseconds. So the introduction of eNVMs will significantly improve the bandwidth requirements or bandwidth mismatches between DRAM and NAND flash. Why is this possible is something that we should think very carefully. At the system level, remember, NAND flash was completely sequentially driven storage, whereas DRAM was random access, right? And that is why the sequential access also caused a lot of the latency issues. The goal in eNVMs, as you will see from their names, RRAMs, MRAMs, PCRAMs, they are all RAMs. They are all random access memories. So the idea is to have random access in eNVMs, therefore improving latency, other than the advantages you get at the device level. Also, you want to have non-volatility preserved in eNVMs despite having better latency. And this is the key benefit of eNVMs, that you will have equivalent to DRAM or little worse latencies and performance, but you will have non-volatile storage. And the final thing which seems very lucrative in the case of eNVMs is the power burn. And this is what we will speak about in a little bit of detail. I have noted over here that DRAMs generally had very high power burn. We gave the reason that charge is continuously leaking out, so you need to refresh. That causes a lot of power burn. Whereas NAND flash, once you store the information, you don't need to keep refreshing, so it helps in power. But remember, NAND flash is still a dynamic element. It's a dynamic transistor. That means it consumes power, it leaks power even when it is shut off. And this is the key value addition that eNVMs, especially two-terminal eNVMs, promise to bring in the picture. The idea is you will be able to resist this or contain this power burn by having passive two-terminal elements. And this is a very good introduction to now move past active three-terminal devices. Remember, everything including your SRAM, your DRAM and NAND flash all involved active three-terminal transistors as an integral part of the memory or storage device. So question people started to ask is it possible to build a passive two-terminal memory or storage device. Okay. And the first answer came from Leon Chua. Before that, we will again try to revise why is it very important to build two terminal passive memory devices, because it will have two main advantages. First is low power. The idea is that you will not have leakage during static conditions, or you will not have static power loss. The other is regarding scalability. Common sense suggests that going from 3-terminal device to 2-terminal device, if you remove one terminal somehow, the cell area will shrink and your minimum feature size f will also shrink. And in this slide only, I will give you an evidence for that. So that is the promise. So this is why people started looking at passive 2-terminal memory devices. And the first proposal came from Professor Leon Chua, who was from Berkeley in 1971, as early as 1971. And this was a very interesting theoretical search into something called the memristor. Now, this memristor is something that we will now look and study. What is a memristor? Memristor is exactly this. It's a passive 2-terminal memory or storage device. So how did he go about doing this? Actual details are a little bit more mathematically rigorous, but for our purpose, let's look at it in a simpler fashion. So if you know, any electromagnetic circuit will have 4 main parameters. One is your voltage, electrostatic potential, or the next is your current. The third is your flux, magnetic flux, and your fourth is your charge. Of course, all these are interchangeable. If you integrate current, I dt integral will give you charge. So integral of current gives you charge. Similarly, integral of voltage over time gives you flux. Okay. And also we know that there are 3 elements which we study continuously, and we also use it in our lab, which links voltage with current, current with flux, and also voltage with charge. So what is the element which links voltage with charge? It is your very simple capacitor. We know Q is CV. Okay. What is the element that links voltage with current? It is your resistor. Resistive element dV is equal to RDI. What links your electrical current to flux? It is your inductor. Your inductance or inductor d phi is equal to LDI. Out of the 4 parameters that characterize a electromagnetic circuit, we saw all are interlinked to each other. Only there was one missing element. One missing element was a device or a 2-terminal passive element that could link flux to charge. And Leon Chua proposed that a element which links flux to charge, indicated by this letter M, d psi will be equal to M dq, will have very, very interesting properties. The interesting properties it will have is it will be a memory resistor, or in short, if you just concatenate both the terms, memory and resistor, it will behave like a memristor. And we will see what is the meaning of this memristor. Simple way of looking at it is, remember, d phi is equal to M dq. The interesting thing about this memristive element is that this M is not just a simple function. It's not a constant, but it's a function of Q. This is what makes things very interesting. We can replace d flux with V dt and dq with I dt, and we can just very naively cancel out the dt, and we will see that just like the capacitor was a phase shifted analog of an inductor, similarly the memristor is nothing but a phase shifted analog of your resistor. And that is what makes things very, very interesting. Now, if just like an ordinary resistor, the value of R was constant and not changing as a function of V or I, this would be a simple boring. A memristor would be a boring resistor. But what makes memristors very interesting is the value of this M is not just nonlinear, it also becomes a function of charge. So M becomes a function of charge. And we will study more about this in the next slide. But just to complete our historical perspective, although the first theoretical observation or theoretical prediction for memristor was made in 1971, only in 2008 in HP Labs, the first practical demonstration by Stanley Williams Group was shown for the memristor. So here we see that a memristor is exactly what we want it to be. It is a practical two-terminal device. What is this two-terminal device? You have one electrode to be platinum, another electrode also to be platinum. In between, you have an oxide TiO2, titanium oxide. And this shows very interesting memristive behavior. How can we say this is a memristor? You see, it shows very simple resistive elements. In this curve and in this curve, we see that the current is proportional to the applied voltage, roughly linear, mostly looks like Ohm's law. However, there is also a very interesting thing called hysteresis. As you can see, this memristive element shows hysteresis. Remember from our study of SRAM, whenever you start seeing hysteresis, you should know that there is a possibility that this element can behave like a memory, and this is what we saw in a simple two-terminal passive element. And this was the great breakthrough. For the first time in human history, people physically or experimentally had shown that a two-terminal passive element can behave like a memory device. And we will see in the next few slides why it behaves like a memory device. But before that, let's address the point of scalable. So here I would want to draw your attention to this AFM image. So very tiny AFM image. Can you see a memory element in this AFM image? There aren't one memory element. In fact, there are 17 memory elements in this very small footprint. So this is your bottom electrode of platinum. This is your top electrodes going like this. These are your top electrodes of platinum. All are segregated with each other. And there are 17 such cross points. You can count. There are 17 such cross points which are embedded in a very small area. And each of these cross points have a characteristics which looks like this. So in a very small area, very small footprint, very small minute footprint of a cross point, the cross point between a bottom electrode and top electrode, you are able to make a memory element. And this is why this was such a big breakthrough, that now there is a promise to make scalable, low power, two-terminal passive memory elements. Okay, now let's go back to our original question. Why does this nonlinear memristor, which is a function of Q, why does it give a memory effect? To answer why it gives a memory effect, we have to learn something about the pinched hysteresis loop. What is the pinched hysteresis loop? Let's first look at what is hysteresis. From our study of SRAM, we know the meaning of hysteresis is that the path the IV characteristics follows on the wave front, this is the forward sweep, is not the same that it comes back in its reverse sweep. So this is the forward sweep where you are increasing voltage. You see, this is the path that is being followed. On the return, it is not following the same path. This is the meaning of hysteresis. And you see that it follows the same thing whether you apply positive voltage or negative voltage. So you see a hysteresis in the positive voltage also. You see a hysteresis in the negative voltage also. The meaning of pinched hysteresis is that At V is equal to 0, I is also equal to 0. And this pinched hysteresis is very important because we are dealing with passive elements. Remember, passive elements can have the IV curves only in the first and the third quadrant. And at V equal to 0, I should be equal to 0. Otherwise, it will be a power consuming or it will be a power generating device. Because you have pinched hysteresis, you're sure that this is a passive element. Now let's understand why are you getting this pinched hysteresis with a simple example of a water pipe. Let us look at the example of the so-called memristive pipe. In the memristive pipe, what happens is initially you take a normal pipe and you had a diameter of D0 and you are now going to flow some water through the pipe. So in this magical memristive pipe, what happens is when you flow water in the positive X direction, the diameter pipe increases. And as a result, for the same pressure of water, now you have a different flux. The flow of water increases because the diameter of the pipe has increased. Therefore, psi2 is greater than psi1. However, what is very fascinating about the pipe is that the expansion of the pipe is plastic. It is not elastic. What is the difference between plastic and elastic? Remember, plasticity is you pull a plastic rubber band and when you remove the force, it comes back to its original position. That is not what is happening here. Here it is not elastic, it is plastic. It means once you apply some force, even after you remove the force, the state of the system remains in that position until you revert it back by applying an opposite force. And in this case, what you do is you flow water in the opposite direction. When you flow water in the opposite direction, the diameter again shrinks back in this magical memristive pipe into original D0. So for the same pressure, again you are returned back to its original flux. First thing important to notice, for pressure, when you apply no pressure of water on the pipe, the flux will be 0. This is what we talked about the pinched hysteresis. Also, we will see that for a fixed P1, either you can get a flux of psi1 or you can get a flux of psi2. The flux can be small, that means it is in its original position or normal state, or the flux can be large. That means the pipe is in its expanded state. And this is where the property of memory comes from. This memristive pipe exists in two distinct states, the normal shrunk state or the expanded state. How did you go from shrunk to expanded and back? By controlling the flow of direction of water. Direction determines. So if it is in the expanded state, it means it remembers that previously water has been flown in the plus X direction. If it is in the shrunk state, it means it remembers that water was flown in the minus X direction. Now with the same example, we will transform the pipe into a resistor. Let's now look at the same effect now in a memristive device. So this is a memristor device which initially has some resistance. Just like in your pipe example, you flow current in positive plus X direction. Now let's see what happens. In this graph also, you are flowing current in the positive X direction. When you flow current or charge in the positive X direction, if the resistance had to remain same, this would be a linear line. But as you can see, as voltage increases, the current is increasing. What does that mean? If current increasing means dynamically the resistance is changing, the resistance is shrinking, the resistance is becoming smaller and smaller. And therefore, on the way back, you see because the resistance is reduced, for the same voltage, you are getting much higher current. For the same voltage, which is on x-axis, earlier you had a small current, now you have a larger current. How do you revert this back? You flow the current in the opposite direction. Now you are in an expanded pipe or shrunk resistance state. So what do? You flow current in the opposite direction. And as you flow current in the opposite direction, you see dynamically that the resistance of the memristor is increasing. How do you know that? Because the current is dropping. And therefore, for the same voltage in the reverse sweep, you had larger current. Now, in this forward sweep, you are having lower current. So, the resistance has gone from a low resistance state to a high resistance state. And exactly at V equal to 0, you cannot have any current because it's a passive element. So, at V equal to 0, I is also equal to 0. However, as we discussed, at a fixed V, if we fixed V, you can have two conditions. One is I is small. If I is small, it means it is in the high resistance state. Please note these terminologies very carefully. So this is the memristor in high resistance state. How do you know it is in high resistance? For the same voltage, you are getting lower current. That is why it is in high resistance. Or for the same V fixed, you can also exist in the low resistance state. And this was your low resistance state or LRS. So this HRS and LRS is some terminology that we will keep using throughout when we study ENVMs and memristors. The last thing that we will study today is the transition from high resistance state to low resistance state. So transition from HRS to LRS is generally known as set, whereas the transition from LRS to HRS is generally known as reset. Why is this terminology? It is very simple. Generally, as you even saw in the example of your first memristor from HP Labs, the element in between or the material between the two platinum electrodes, metal electrodes, was TiO2. Now TiO2 is an insulator. So memristors generally are made out of the active element is a insulator. Therefore, naturally it is in high resistance state. So moving from a natural state to low resistance state, natural high resistance state, or as fabricated high resistance state to low resistance state is called the set. And taking it back from low resistance state to high resistance state is called reset. So please remember these terms. Low resistance state, where the memristor flows a large amount of current. In high resistance state, the memristor flows very small amount of current. And the transition between HRS and LRS, which is set, and LRS to HRS, which is called reset. Okay, with this, let us conclude our class, and in the next class, we will begin our study with a very interesting question. What is the mechanism through which a material goes from HRS to LRS and LRS to HRS? And how can a material do it repeatably? Thank you very much for your kind attention.